بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه وسلم. Today we are. Can we switch this one off, please? Yeah. Today we're happy to have Dr. Mohammed Zuki Yusoff on his seminar, Extraction of Brain Signals for Assessment and Control. Very short bio about Dr. Zuki. He's an associate professor at Universiti Teknologi PETRONAS UTB, and he is also the head of the Center for Intelligent Signals and Imaging Research, CISIR, and a member of the Institute of Health and Analytics, IHA. Dr. Zuki has accumulated over 29 years of experience working with various industries and academic training institutions. He graduated from Syracuse University in New York with a bachelor degree in electrical engineering in December 1988. He completed his master's in England from September. He completed his master's of science in communication networks software from Surrey University, Guildford in England in September 2000 to September 2001. He obtained his PhD degree in electrical and electronic engineering from Universiti Teknologi PETRONAS in February 2010. His area of PhD study was on brain signal processing. He is currently undertaking research in brain signal processing, event-related potentials, brain-computer interface. He has numerous publications and patents, and he is leading several research projects. Please welcome Dr. Zuki.
Thank you very much. Thank you to Professor Obaid. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So my topic of today will be the extraction of brain signals for assessment and control. Okay. Actually, I have two different lectures. One is on the estimation of visual evoked potentials for measurements of optical pathway conduction, and then another lecture is BCI for wheelchair control using some DWT and also ITD methods. BCI stands for brain-computer interface. So for lecture number 1, estimation of visual evoked potentials for measurement of optical pathway conduction.
Okay, it's here.
Sorry?
Left, right. And if you want this left and right. And left and right.
I have to flip this.
This is for the
Oh, okay, all right. VEP is actually used in hospital environment. Visual evoked potential, it is called. It is an objective test to actually assess the integrity of our visual pathway right from the retina all the way to the occipital cortex area of the brain. So normally doctors will use this objective test to actually assess whether the crisscross connection from the retina to the occipital cortex area is still very, what we call, good, or it has got some issues. And normally to test this particular visual evoked potential, we have this particular black and white checkerboard where a subject will be placed in front of a computer screen, and the pattern black and white will actually take turn. The black will change to white, and also the white will change to black from time to time at a predetermined period. And then once the black and white change colors from like white to black, black to white, the subject will register a particular signature inside the brain. I call it as a signature. But this signature is not easy to extract because the ongoing background noise is there. Everything that the human is thinking at that time, apart from the registered signature, will be considered as noise. And this particular ongoing or background EEG, electroencephalogram waveform, is actually larger than the one that we are interested in. The one that we are interested in is the visual evoked potential. So the challenge here is, of course, to try to extract this particular visual evoked potential. Inside a hospital, normally doctors will use equipment, and this equipment is designed to accumulate a series of EEG waveforms, for example, 100, 150, and then the waveforms will be added together. So this method is called ensemble averaging. And then at the end of the day, one particular noise peak, it is not really a pure sinusoidal wave, but it looks like we have like a waveform there. And the peak, the first peak is available around P100, they call it. This is like 100 milliseconds after the signal is changed from the light source to an electrical signal near the retina area. And then the traveling time taken from the retina all the way to the occipital cortex area for normal persons will be around 100 milliseconds. So if those subjects, sometimes they involve in some we call mishaps, say accidents, and then they went to doctors for checkup, normally the P100 doesn't occur exactly at 100 milliseconds. So it can occur around 120 milliseconds, for example, for the positive peak, P100. So the challenge for us is actually to try not to use the ensemble averaging method. We want to take, for example, for the first waveform, and then if we try to apply our proposed technique, then this particular first waveform can be what we call cleanup. We want to remove the ongoing EEG from the what we call desired visual evoked potential. So what we propose will be called the generalized eigenvalue decomposition. It's better?
Yeah, better because
okay.
of the reflection there.
So we can see here from this particular checkerboard pattern, alternating black to white, white to black, and then the subject will stare at this particular computer screen, and then a particular signal will be registered. And then the waveforms captured will be the visual evoked potential added with the ongoing EEG background. And normally the EEG background is much higher, the noise. This is what we call the noise. And we want to employ a signal processing technique to actually extract this particular VEP from the overall corrupted waveform. So as I mentioned, in hospitals normally when clinicians or doctors purchase equipment, the manufacturer will utilize the normal ensemble averaging instead of a fancier technique. Trial 1 will be added with trial 2 until we have trial N. So this is like 100 or 150 or 200 different trials. And then at the end, this particular peak will be visible to the eyes. So what we want is actually to just take trial 1 and then process the trial 1 or the trial 2 alone without having to add one trial after one trial after one trial. Okay, so I think I have covered this particular concept. The idea here is actually to see where the location of the P100 is, whether it is at 100 milliseconds or 110, 115, and so on. And then we also have some current techniques proposed by other people. And such techniques, I just chose like 3 here. one is called subspace regularization method by this particular author, and then third order correlation by Professor Garib. And friends, this was coming from his work while he was in Riken Brain Institute in Japan. I think now he's back in Egypt. And then the third technique is called the subspace dynamical estimation method by another author. So the theory will be, the model is developed in such a way that the corrupted signal is equal to the wanted signal plus noise. So the X will be the one that we actually want. So we employ this particular minimization technique to actually formulate, and then at the end we'll get this particular X. The idea here is like we optimize by minimizing instead of maximizing. Minimizing means we want to minimize the error that exists.
Question.
Yes, yeah.
Usually, in such signals, we usually have a component for physiological noise because it's colored noise, and another for the random noise. So you
Yes.
have both in one end.
Yes, yes. So the challenge,
They're very different.
the challenge here is like we treat noise as colored noise, not like Gaussian white noise. So it's very difficult actually to remove the noise because the colored noise tend to be present within the what we call bandwidth of the wanted VEP signal. So at the end of the day, when we want to try to minimize, then we'll involve this particular formulation using a Lagrangian function involving Kuhn-Tucker method. And then also we involve the eigenvalue decomposition. We can try also using the other, what we call similar method. Instead of using eigenvalue decomposition, we can use SVD, singular value decomposition also. So in the end, we have matrices. This is like the format for the eigenvalue decomposition, where this particular G is like the gain that we actually want. It represents the eigenvalue, and then the V actually represents the associated eigenvectors. So this is actually the last formulation. We want to find the approximated required or clean signal by the means of this. So involving this particular eigenvalue and also eigenvector matrices. And then I think I have just to skip these particular slides. For my study, I actually simulated the particular VEP signals to include not only the positive P100, but also to create other peaks at 200 milliseconds called the P200, and also at 300 milliseconds called the P300. And then these are actually my simulated waveforms, P100, P200, and P300. So these would be considered as clean VEP signals. And then I can simulate the noisy signal by actually adding it with some noise. And then I can control the level of noise. So I varied the signal to noise ratio. It doesn't appear here, so should appear, but something is not right. Probably the color. Yeah.
I can see it.
The corrupted signal should be there, but some of us may be able to see.
I can see.
So in the end, using our technique, we can somehow recreate the wanted VEP signals. But this is by means of simulation. And for this instance, the situation is the signal to noise ratio is at -7 dB.
How do you model the noise that you add here? How do you put a model for the noise?
We use some auto-regressive kind of techniques. Of course, this is not developed by us. It's utilizing some available kind of techniques. So this particular auto-regressive technique has been what we call EEG kind of creation, has been proposed by some what we call researchers. So I just adopted such techniques.
And when you compose using the SVD or whatever the ideal composition, you usually look for a subspace for the noise and a subspace for the signal.
Yes,
How
yes.
do you identify them in the eigen decomposition?
We tried several ways. With the one way is like we try to just take care of the non-zero values of the eigenvalues of the diagonal elements.
Usually, no zero eigenvalues usually. You have a realistic signal, usually you don't have any zero eigenvalues. You usually have very small values, but they're never zeros. Basically, you have colored noise, you usually have much larger values than zeros.
Yeah, we have like some, in my study, negative kind of values. So those negative eigenvalues, we actually, omitted for our consideration. So we just keep the positive values.
But when you try with SVD, you never have negative values.
As far as I can remember, I did have. I did have.
The singular value.
Singular value, the composition you would not
And
have.
singular value, they are positive. Eigenvalues, it could be negative, it could be positive.
I think you tried the eigenvalues here.
Eigenvalues, yes, eigenvalues. Thank you. And this is actually with regards to the extraction of the peak P100, P200, P300, and then the performance matrix is measured by means of average errors versus specific signal to noise ratio. So I tabulated the what we call performance for P100, P200, and also P300. So the errors and also the failure rate are as per the list. So this is mean latency versus SNR. And also standard deviation versus SNR for 3 peaks, P100, P200, P300. And of course, for comparison purposes, we recreated the techniques proposed by Karjalainen, the subspace regularization method, and also the third order correlation method. And one more is the subspace dynamical estimation method. So in the end, still have a problem with the corrupted VEP. So we have this particular extraction performed by our proposed technique, and these are the extracted signals using the SRM, third order correlation, and also subspace dynamical estimation method. And we took at one particular SNR value, which was at -8 dB. This is like even worse. It is simulated at -10 dB. I'm sorry, couldn't really see the corrupted VEP here. still the eigenvalue decomposition approach could retain the integrity of the P100, for example, more or less to be around 100 milliseconds. And then these are some tabulation with regards to average errors, failure rate and latencies, together with the standard deviations for P100. So the color is not really bright. So we can see that the proposed technique, generalized subspace approach, the variations in terms of latency is narrow compared to the other techniques. So this is for P200, P300. And we also took data from real subjects. So I went to one hospital in Kuala Lumpur. So our place is about 220 kilometers away from Kuala Lumpur. So every week, I mean during my, what we call study, I actually drove down from my university to Kuala Lumpur, and that hospital is called Selayang Hospital in Kuala Lumpur. So I managed to gather around 50 subjects. And then we applied our technique to actually see whether the technique was able to capture the latency. But for hospital, they are not really interested in the P200, P300. They are just interested in the P100. So in this case, for real subjects, I just expected the P100. So this is actually, again, the color is not clear. Corrupted VEP, can we see? Okay, maybe as a summary here, using the ensemble averaging, what the printout gave from the hospital equipment, it gave the P100 value at 119. So the corrupted VEP was showing it at 122. The corrupted VEP maybe is like somewhere here. So this is the 119 that will be used as a basis to evaluate whether the subject is showing normal brain pathway value or not. But in this case, it reflects that it is something wrong with the subject. So if I'm not mistaken, this subject just had like an accident and he didn't feel right. So he went to see a doctor where the doctor measured the P100 and it turned out to be 119. So according to the doctor, anything higher than 110 milliseconds for the P100 will be considered as abnormality. So the GSA technique was showing 118. So in terms of error, it's like 119 minus 118. So it's like a difference of 1. But the other techniques, the differences will be like 3, 9, 14, for example, in this case.
How many trials were used to get that your technique? How many trials as compared to the ensemble average?
Okay, for my techniques, actually, I can take from trial 1, I can take from trial 2, for example, or from trial 3. In hospitals, they took at least 100 different trials, as I mentioned, and then they assemble all the trials together.
So you use one trial?
Yeah, so I can pick like from trial 1 or trial 2 or trial 3, for example. Of course, some variations may exist because for human, the inter-trial variation cannot be what we call prevented. So it occurs. But I did do some what we call checking, and then still, you know, the errors will not go beyond like 5.
So how about the variance? Variance of this variation?
The variance,
I mean, if you use different trials, how is the variance among these trials?
Yeah, so I just took some what we call average mean error. So if I have 100 different trials, I go to trial 1 and I jotted down what is the difference. I go to trial 2, I jotted down, what is the difference. And then later, I just took the average. So this is reflecting, the error using that particular average. So the standard deviation is measuring, how far the signal actually deviates from the truth. Here I'm just showing up to subject 26. But to be complete, I have up to 50 different subjects. So the subjects were labeled as S1, S2, S3, S4, until S50 actually, but I'm just showing S26 up to S26. So here, the lower the value, it means the better the performance.
In this case, means you're taking the result of your technique as the standard, and then you are comparing with the ensemble average. Is that
I'm using the ensemble average as the reference point.
is that
Yeah, because there is no way to actually tell without using the ensemble averaging
the existing?
what the P100 is, for example. Because looking from the single trial alone, it is a lot of noise. So we cannot deduce whether the P100 occurs at 100 millisecond or not. That's why manufacturers normally they play safe by lumping, averaging all the waveforms together.
Generally, what is the trend? Means the actual peak that you got, is it always before the average peak or
The trend, good question. The trend is normally above 100 milliseconds, say 102 millisecond, 103, 105 milliseconds, for example. So this is actually translated into some journal papers. We got one transaction paper, IEEE transaction in biomedical engineering, and then some other journal papers. And for this work also, we managed to file one patent, and it was like granted with the Malaysian patent agency. Okay, so this is the lecture number 1 for extracting the EEG for what we call assessing or diagnosing the health of a subject. Yes, please.
My question, maybe I didn't catch the importance of P100, P200, and so on. My question now, since you are searching for this type of, I could use filter banks maybe, which is like wavelet transport to detect these, because you are searching for the 100, the 200, and so on, right?
Yeah, yes.
So it is sort of filter banking, right?
Yes.
So wavelet should work, I mean, in these things.
We can try also using wavelet. Yeah, but during my study, of course, I didn't venture into, wavelet kind of approach. So I wanted to just use this, what we call, this is like from the time domain perspective alone. Of course, wavelet can cover both frequency and also
But again,
time domain. Yeah.
my question is, what is the importance of P100, P200 in the diagnosis, in the medical diagnosis?
Okay, the P100, of course, is very important in the clinical kind of environment for the doctors to assess. Say, if we take a look at one object, so this object is actually by means of light signal. So the retina will change the light signal into an electrical signal. So using the VEP test, the doctor wants to see how long will the electrical signal travel from the retina to the occipital cortex area. So our eyes, we have like crisscross connection, like this. So the left eye has what we call a pathway, brain pathway, from this, say, left side of the eye to the right side of the brain.
Okay. But the
And
delay,
so on.
The delay.
The
let me
delay-
call it the delay.
Yeah, the delay.
I mean, what is the tolerance of this delay that we can say this is normal and this is not normal?
According to doctors, I interviewed like several doctors who are specialists in this under the Department of Ophthalmology. So they say anything less than 110 is still okay. Is still okay. So if 110, 115, 120, then they say start to be concerned because the integrity of the brain pathway has been compromised. That's the statements from these particular doctors.
Maybe we can have one or two questions.
Actually, okay. In radar imaging, basically the optimal solution is usually basically taking a bank of matched filters and basically checking which one is got the best match with the signal that's coming. Since I know how it looks like. So did anybody try matched filters? Since you know exactly how the P100 looks like.
We know that there will be like a peak, around the 100 millisecond, but I mean, based on the corrupted signal alone, how to actually tell?
Because actually it's matched filters, so basically it's going to be better than another matched filter in another place. So basically compare the different places of the matched filter, and basically the peak will give you the location of the P100.
It's probably it's gonna work also. I haven't tried actually. So
Maybe we have
it may work also. Yeah. Thanks. Thanks.
Go to the second. Maybe.
So okay.
I have one quick question. When you do eigenvalue decomposition to find the subspace for the noise and the signal, but you mentioned in the beginning that the noise part are dominant in compared to the VEP.
In reality, the noise part is higher than the VEP signal.
So when you do the subspacing, how you decide, because the dominant part will come by the noise, how you will decide this is coming from the signal or from the noise? Because eigenvalue will be dominant by the noise part.
Okay, I employed also, apart from just filtering out the non-positive values, of the eigenvalues, I tried also using the so-called archaic information criteria, or archaic information criteria, So only several diagonal eigenvalues are actually chosen using the archaic information criteria. It's not like one value or two values, like several values, So using this AIC, archaic information criteria, the performance is actually better than just having non-negative values alone as a basis.
Okay. What is the criteria of this archaic value criteria? What is the basis of this archaic value criteria?
Statistical.
The theory is a known, very famous technique. Yeah.
Because of the time, and also, Doctor, I have to make one comment actually regarding what Professor Yasser mentioned regarding the singular value decomposition, because if you model your system as a linear system and you did some sort of techniques related to SVD, then actually maybe we do this one and sometimes called the gradients. Sometimes actually the singular values actually give you a very good indication, and at one point in time you notice that there is a break in the singular values of the system, not of the matrix. And this one you can separate the maybe noise from non-noise. It's very clear, and it is really related to the it's actually do some sort of decoupling in the part of the system. It actually breaks the system into maybe two or more. And this one gives a very excellent measure, and also you can see this also in terms of norms, H infinity norm and these things. So maybe this is another way. Maybe the last question was with Dr. Khalid, because we need to go.
Okay, I have a couple of questions.
Yes.
First is, maybe I don't know it very well, but what I feel is, how do you differentiate that, let's say, a person who got some sort of accident, okay, and you are seeing some delay. Or it could be that the person is drunk or is sleepy. This could also cause, I think, similar type of effects, because the reflexes, they get lost, they get delayed. Am I true? Or?
Yeah, that factors, I have not actually encountered statements saying like, if such a person is drunk, then the traveling of the signal will be delayed.
No,
so,
but is there a study on this thing? I think it should.
Actually, consciousness has nothing to do with this, because this is actually a reflex. This is a neural reflex. So basically, it happens the same way whether the person is awake or not awake. So basically,
no, but it is the path delay.
Yes,
even
high order processing that actually is affected by such conditions. High order processing.
So basically,
after the signal goes to the brain, actually it's affected by such things. But actually,
in the way it is not okay, and they are measuring it in the way. That's what it is.
No, but these type of things, for example, even means intoxication. I think this could cause these type of delays, isn't it? But this goes in
actually, they actually affect the way the conduction happens. This is different from having the process.
Yeah, even for the conduction means these different type of agents. They actually change the release of these ions, isn't it? That transmit the
monkeys actually, and we basically put these stimuli in front of them, and we get the signal. Basically, they would be sedated.
Yes.
He's not conscious.
So it is proven experimentally that this is the case. Okay. That's what you're saying.
Second question is that, okay, you are saying that, okay, the signal of right eye goes to the left part of this.
It's a crisscross kind of thing, yeah.
Did you study both areas separately?
Well, I just have to rely on the, what we call facts and figures by the clinical sites, So the concentration was only to tackle the problem from electrical engineering point of view. Of course, there are constraints here and there.
No, means if both sides they are receiving signals.
Okay, you mean...
They have this signal, they have both of them, they have electrical signals.
Okay. Yeah. The doctors will actually assess the eyes one at a time. So if the left eye is to be assessed, the right side has to be closed. Yeah, there is a patch to close, what we call one side which is not being assessed at a time. So it is performed separately. Say the left eye first, and then later the right eye. So it's not like all together, at the same time.
Okay, maybe you can continue quickly on.
So due to the constraints of time, I'm given only 1 hour, Professor, right?
Yeah, maybe you can speed up the thing.
Yes, so this one is actually, we wonder whether if we use currently available techniques such as discrete wavelet transform and also one more known technique.
Maybe you can come to this side because of the...
Sorry again, yeah.
That's okay.
One more technique is intrinsic timescale decomposition methods, just to see whether these particular two techniques can actually what we call extract some features which are meaningful for what we call initiating commands. Say, for example, if you want to control wheelchairs, we can maybe create a command to go forward, to go left, right, for example. So we ask subjects to actually imagine moving, say, for example, their right hand. Not actually physically moving it, but just imagining it. And the imagination of movements is called a motor imagery kind of what we call concept. Of course, prior training will be done by asking the subject to actually do real movements. So once the person gets the hang of it, then later the subject is expected to only imagine moving such right hand or left hand or both hands or both feet, for example. So if you want to create a 4-class kind of situation to control forward, left, right, say back, for example, then we need to involve right hand, left hand, both hands or both feet. And then we can map, maybe right hand is for forward, left hand is for something left. So that one is like arbitrary. It depends on the designer later. So in terms of the area is under the mental, what we call state strategy, we are using this motor imagery. And then ERS, this stands for event-related desynchronization, event-related synchronization. And from the literature, it is a known fact that for motor control, the area of the brain is the middle area called the C3, CZ, and also the C4. So up to now, of course, it is still challenging to do the mapping between the designated mental task to a specific, what we call direction to be controlled. So the wheelchair can always be replaced with some other devices. For example, here probably drone kind of thing is relevant. So the what we call work here was just to try to use those DWT and also ITD techniques to actually see whether such unique features exists when people imagine moving right hand, in comparing it when people imagine, the left hand movement and so on. So, the overall process is like this. And then in terms of experimental design, a subject will undergo this particular process. There will be a duration where the subject is asked to just calm down, relax without imagine something, and then later he or she will be guided. So if he sees this, then this is like trying to imagine a particular what we call movement. And for this particular experiment, one run will actually take that so many seconds, so 2 plus 3 plus 1.5 plus 3 plus 2. And then in this case, 5 different runs have been what we call undertaken. And then DWT together with ITD have been employed. So in the end, they were compared among one another. So the what we call frequency range of interest will be covering this particular value. The alpha is within this frequency 7.81 hertz until 15.62 hertz, and the beta is this one. And for ITD, I mean, this is like involving proper rotational components kind of thing. ITD, as they claim, is good to deal with non-stationary and also non-linear kind of what we call situation, which DWT may not, be able to do such a job. So some optimization processes have been actually introduced in the DWT and also in the ITD. And then in terms of the topographical distribution map, this is like showing when the right hand is being imagined, then the concentration of the brain is like to the left. And then this is like for left hand imagination. Then the activity is like to the right. So this is the frontal part of the head. And then this is the left part, right part of the head. And then when both hands, sorry for the spelling mistakes. For both hand imagination, like imagining, moving both hands. So we can see like 2 areas inside the brain are active. And then this is both feet have been imagined, then the activity was showing somewhere in the middle of the brain. So this is what we call the sensitivity versus specificity plot without region of interest. But then once optimization has been performed, so we could see that the value increases. And then this is the performance taking 35 subjects into consideration in terms of the classification accuracy, sensitivity, specificity, and so on. So this DWT and ITD have been compared with some other techniques also by other people. I mean, of course, we do not claim that these original or really novel kind of techniques coming from us. We just like wanted to try whether these particular approaches will outperform these other techniques here. And ITD has been found to have less computational complexity.
This comparison on a particular data set, the same data set for all of them?
Yes.
Usually these people work on the PCI competition data sets.
For our case, we got to recreate and then test, the data from the subjects. We apply the data from all our, subjects.
So you implemented
to the individual EMD AR and so on.
Sometimes the experimental conditions are different, so basically it's better to use the PCR conditions because it's actually verified by several groups.
Yeah. Good suggestion. But in our case, we didn't utilize, the what we call public data sets. We just wanted to see whether from our own subjects, how the individual technique performs. I mean, probably like later, this can be tried using the readily available public data sets. Okay, so the ITD is performing well in terms of the computational time. So that's why people say the ITD is a suitable kind of candidate for close to real-time kind of what we call application, because like this one is still taking much longer. So for offline analysis is okay, but for online kind of analysis, some drawbacks encountered.
I have a comment on that.
Yeah.
Because actually you collect the data in 3 seconds. So basically it doesn't really matter if you have like half a second, additional half a second, while you acquire in the next 3 seconds.
Mm-hmm.
Right? Because the data collection is much larger than computation.
Mm-hmm.
So it's probably not that critical.
Okay. Good observation. Thanks. So this is like the conclusion. I mean, like, the ITD outperforming the algorithm, other algorithms, such as DWT in this case. The difference is like around 6% in terms of the accuracy of classification. So if you don't mind, Professor, can I take just maybe a quick one, just to introduce my center?
Yeah, okay.
Just maybe I will just make it brief.
Yeah, okay. Why not?
Yeah. So I'm introducing my Center for Intelligent Signal and Imaging Research, CISR. This is under Electrical Engineering Department. So I'm heading this particular center. Professor may remember last time it was Dr. Naufal.
Yes.
Dr. Naufal now is in France. He's being assigned as an international liaison officer for the European kind of what we call community. Okay, so I think I don't have to go through this, right?
Yeah, because of the time.
Yeah, because of the limitation of the time. So mainly we are an engineering university. We have all the programs under engineering, electrical, mechanical, civil, and whatnot. So I'll skip. We are actually under this particular Institute of Health and Analytics, now being directed by this Associate Professor Dr. Tang. So apart from this Institute of Health and Analytics, we have some other institutes as shown here. So CISR has been established in 2008, and then somewhere in August 2012, CISR has been recognized as the Center of Excellence within the university, within Universiti Teknologi PETRONAS. But in 2014, October 2014, we had been awarded a national, this is like Center of Excellence status nationwide by the Ministry of Education. So with that, of course, we are entitled to receive some annual, what we call funding from the Ministry of Education to support our research activities. So the aspiration of our center is actually to be, we call, very good in neurotechnology. And the aspiration is, of course, to target social, work, health, and safety, we call, aspects. And the tagline for our center is this: neurotechnology for brain assessment and intervention. And you can see the functions of our center, and then we have national and also international collaboration with universities like King Abdul Aziz University is also there. And then I think this is just like some histories. I think we can skip this. So now we don't have that many people, but we rely on this number to actually comply with the national requirements. The publication from the ministry is 20 journal papers per year, the Q1, Q2 journal papers. So on average, if you have like 1, 2, 3, 4, 5, because we declare to the ministry, at least they require around 5 core members. So they will just multiply. 5 by 4 will be 20. If we declare more, then they say like 6 by 4 will be 24. If you have 7 here, then they say 28. So, I mean, we just play safe. So up to now, alhamdulillah, we managed to still, like get at least 20 papers per year. And our, what we call area of research is, this is part under brain pathways and also mental states. So for assessment, we are doing research related to cognitive ability, learning, addiction, and then this is under brain pathways. Under mental states, this is assessing the workload of brain, and then stress, fatigue research, drowsiness, sleepiness, distraction, wellness, calmness, thoughts, etc. And also, we do also some neurofeedback kind of, we call activity under this intervention. So our pledge to the ministry for research areas, now we pledge to them that we will undertake some learning kind of research and also research related to stress, to measure stress at a workplace. The equipment that we use is normally coming from EEG equipment, but it's not just constrained to EEG equipment. We also have these other machines, FNIRS, ECG, fMRI, and so on. So these are some photos showing our FNIR machine. This is coming from Hitachi. So we have 2 units, right, Dr. Saad? 2 units. I think one costs around 1 million plus. And some EEG, portable EEG kind of devices. So like 8-channel EEG, 16, 20, 64, all the way to 128-channel EEG machine. So some other equipment that CSIR currently has. It used to be in the past, we did research not only within the brain, but covering the whole body. But since being given this National Center of Excellence status, the ministry wants us to actually, narrow down to just do research on the brain. But apart from CSIR, we have this particular group called the SMART group, which is under the Institute of Health also. So this is where rehabilitation will be what we call undertaken, like research related to what we call this exoskeleton kind of, we call devices and so on. So some brands that we have in our center. So these are showing the publication quality based on the site scores. And then collaboration. We have King Abdul Aziz, right? Yeah, here. And then in France, we have collaboration with University of Burgundy, and India, Pakistan, also Iqra University, with Japan, Hitachi, Taiwan. I think National University of Singapore also is there. Yeah. So with the University of Burgundy, we have a double degree kind of program. They call it co-tutel or joint supervision for PhD study. So the student will be awarded like 2 PhD degrees, one from the University of Burgundy side and the other is from UTP. Well, this is like to reflect on some we call incomes being generated. So the Ministry of Education will also assess, like once they give funding, annual funding to us, they want to see also the return on investments being what we call made.
Excuse me.
Yeah?
Is generated income mainly from the government or you have it from other places as well?
We have not just from government, we have also from some industries.
What is the percentage? Government, mainly the government, or you have a lot of money coming from industry?
Okay, the industry in terms of the what we call involvement in Malaysia is not really, that high yet. So because the problem is that always they want to see something tangible. But I agree because the thinking should be there, but the doing also must be there. I mean, they don't want to see just publications, but they want to see these outcomes, research outcomes, that can be what we call translated into real kind of prototypes or real products.
More than 50% is from outside government.
From outside government, right?
50%?
Yes, more than 50%.
More than 50%.
Well, even national grant doesn't mean that they're government grants. They are like other national agencies, not government, like PRF and all. They're not government agencies, but they're called national. So more than 50% is outside government.
So we have some internship programs with international universities. So the numbers are there. And these are some of our activities, annual activities, being undertaken. Some colloquium that we have had this year. So this is like with our King Abdul Aziz. So networking with, this is somewhere in Thailand, our director, Dr. Tang, went there. This is somewhere in Kuala Lumpur. I think that is about it. So the bottom line is, like CSIR is open to having collaboration with, say, universities, say King Abdul Aziz University, in the areas of neurotechnology, for example. But we are open also to, say, IoT, apart from rehabilitation. I think this is just like, some extra slides. Yeah, we do benchmarking with some universities from the US, from the UK, for example. I guess that will be it.
Thank you.
Thank you. Yeah.
We will have one or two questions, please.
Assalamu alaikum, Abdurrahman Sabbagh. I'm a neurosurgeon from the Faculty of Medicine.
A neurosurgeon?
Yes.
Okay.
In regards to alcohol, it should not affect nerve conduction unless it causes neuropathy. If the nerve is sick because of the alcohol, and then it's a damaged nerve, and it doesn't, or a temporary damage. But generally, alcohol should not affect VEP.
The delay.
In terms of
It's
delay,
not
it may
affecting the
affect
delay.
the amplitude, but not it would not delay it. Second issue, I just wanted you were saying there was a difficulty in mapping the motor area where you can your either with imaginary signaling is either by the hand area, which is a little lateral, the foot area is in the middle. I think mapping is not that difficult if you use something like, and I'm surprised you don't have transcranial magnetic stimulation. It's not a very expensive device, and I think, you have, because I didn't see the.
Yes, we have.
So if you have that, you can easily, especially if it's navigated transcranial magnetic stimulation, then you should easily find your motor area or supplementary motor area, and then you can use your signaling very easily.
Okay, so.
Actually, with a comment here,
Yes.
it's actually the 1020 electrode positioning.
Yes.
We have particular electrode positions that are not really, you cannot get better than what he had.
Okay.
Because actually, even if you know exactly where within the motor cortex the signal comes from, it's very difficult to get a particular electrode outside on the scan
Okay.
that will get you that particular, it's going to get a whole area that's much larger than whatever
Okay.
specific area that you're looking for.
So there's an EEG array every time you're doing
It's
that.
not like a e-code or something that we
Okay.
actually put exactly on the dura or something, or the dura in the
Okay.
electrode where you actually get from a particular location. Here you get
It's
from a
just
larger
that,
area.
So and the thing is, what I was asking, so what's your next step? You're thinking about putting a microarray on the brain, or these patients you would expect them to wear an EEG, a whole EEG machine everywhere they mobilize?
Because our research approach would be towards non-invasive kind of nature. We will not explore, the invasive kind of thing by implanting chips somewhere inside the brain. But I will take your suggestion, So maybe, with that particular, what we call device, it can assist us also,
He will put it there.
I'm ready.
Yeah. So you are open to collaboration? Thank you. Yeah.
Okay. Actually, this is one of the things, and actually we would like to have ourselves also here.
Yeah,
A lot of collaboration with the College of Medicine. One question, Surzan, here, please. Maybe we could have one or two questions because of the time, actually.
So I will take, all the suggestions, with what we call open, what we call minds, so that improvements can be what we call performed.
Okay, what if the individual have some disease, for example, disorder or neurological disease for the wheelchair that using the BCI? What will happen? Does it will learn the pattern of EEG for this person, for example?
You mean like if a particular person has some
Disorder,
disorder?
yes.
Good.
Let's back on the brain signals.
For the training of
Good
this
questions.
EEG signal.
So as of now, we have not actually, covered that possibility. All our subjects were normal subjects, but for the sake of everybody, it's a good, what we call, strategy maybe later, if some people with disorders, can be what we call included in such an experiment.
Because, yeah, exactly.
Yeah,
You use whatever part of the brain that is not diseased. So if you want, instead of right and left, you can say front and back or whatever signals. And usually people are very trainable when it comes to that.
The last question, the last thing is, with the, you are the best. Put it in there, please. Okay?
Thank you very much. Okay, no worries. To start with, thank you very much for your talks. Very interesting, and certainly you are welcome at King Abdulaziz University. And we are proud that Dr. Ubaid and our team are collaborating with you.
Thank you.
Actually, I have a question about the patent you mentioned. Has it materialized to commercial product?
Well, we have not really, gone that far yet. So this is still, in the conceptual kind of phase. So it is open because as a research center with like 6, 7, people, I mean, we cannot really focus our energy to publish and then to actually, what we call go towards this commercialization kind of what we call
So you're not considering
approach.
commercialization?
As of now, we still have not, what we call produce any commercialized kind of product. But my take will be we need to go towards that direction. Yeah.
And I think UTB is doing a lot, Professor Shahir, and we
yeah.
have actually a collaboration between KU and our patenting and commercialization office here and UTB. Actually, there is some agreement that has been signed a few months ago.
Like sleepiness or drowsiness kind of research. That one is like very beneficial for drivers. So some results, have been what we call produced, but not yet like, towards commercialization. So maybe manufacturers of cars would be, very much interested also in this particular thing.
Okay, I think I'd like at the end to thank you very much for this interesting presentation, and I would like to thank our audience, and hopefully we have another seminar at 1 p.m. and I wish you have the time to attend. Thank you all.
Good to be here.
So,
thank you, Dr. Zuki.
Yeah, thank you very much.
Done a great job, thank you.
Sorry, like some hiccups with the, plot.
I saw everything.
Plot. Wa alaikum salam. Yeah.
Yes.
Yes, both alligator and cat size.
You're welcome. Yeah.
Terima kasih.
Sama-sama.